Yeah, so I'm expecting more people to join in person, but that they may just walk in as they begin. So I suggest we go ahead and get started. It's good that the camera is already zoomed on you. By the way, this is the very last session of this course, and it's sad to see that this is ending and you guys are going to go on your own, and I'm going to be marking up for your last piece, and hopefully we'll remain in touch. But what is very exciting is we saved the best for last.
I don't know.
I'm thrilled that Ross Phillips accepted my invitation to come over to campus and give this guest lecture. Yeah. Those online, just confirm that you're there. I'm going to ask you to turn on your camera. Yeah. Yeah, I was saying, I've heard of Ross for a long time already, and his roots in Saskatchewan, and water issues in Saskatchewan is much longer and bigger than mine. But this is our very first time to meet in person. We passed by each other in conferences, but anyways, I'm very happy to have him now here. And I had a very good conversation with him yesterday just to set this up. He's our own alumnus and graduate of the geography and planning, I think, for the master's degree.
Yeah.
Working with John Pomeroy and Chris Spence. And by the way, I met John Pomeroy this morning.
Oh, did you?
I mentioned to him that Ross is coming to my class. I was, he was one of the best ones. And then he explained what you did with the type of research that he was doing at the time. And he got excited that you're coming here to give this lecture. And before that, you did your undergraduate degree at the University of Regina.
That's correct, yeah.
Yeah. Anyways, then you've been working quite a long time in the water industry with 𝗿𝗏𝗏 Associates first. And, if you don't know 𝗿𝗏𝗏, 𝗿𝗏𝗏 is non-existent, the name anymore, but 𝗿𝗏𝗏 has been always Canadian pride, I would say, in the field of water resources, a Canadian employee-owned company that I got to know during my PhD at Waterloo. And always I heard good things about the environment type of science and practice that they've been doing. And just a few years ago, 3 years ago or so.
Yeah, I think 4 now.
4 years,
yeah.
WSP, another Canadian company that is a mega company in a sense, acquired 𝗿𝗏𝗏. So there used to be a big 𝗿𝗏𝗏 Associates office on the 8th Street here, and now that's part of WSP, my understanding. Anyways, I think that must have expanded your reach in a sense, but these are the interesting stuff that I personally like to hear, hopefully our students as well. Anyways, now, today he is a principal water resources engineer with big influence on the water industry, and my understanding is in terms of modeling as well. And there's a modeling course. You don't have to present anything on modeling in general. We want to hear more generally about your vision, your views, the needs out there, and how we collectively can connect better with the industry. And I'm sure many of these folks may be looking for jobs sometime in the future, so how they can better navigate their career. With that introduction, I'm gonna turn it over to you soon, but I just want to make sure we give some visibility to those students attending online. You don't see them clear.
I can see them on the screen here.
Anyway, so this is a diverse cohort connecting from all over Canada and overseas now.
Okay.
Yes, without any further ado, I'll just pass it to you.
Sure. Yeah, and the thanks for the introduction, Salman. It's a pleasure to come and join you today. And as Salman said, I'm hoping to kind of give a broad-reaching kind of discussion with some introduction of myself, some introduction of like WSP as a company, the work that we do, the projects we're involved in, both locally and I don't know, some a bit of perspective on the broader geography too, and really just scale. I will go and kind of identified a handful of projects that I'm involved in or have been involved in that are really strictly hydrological modeling to give some perspective on kind of how it fits into like different questions. I won't go into all of the nitty-gritty intricacies of like the models themselves and things like that. If there's any questions, I'm happy to answer them, but try and keep it that sort of level and focus more on like our approach, the questions we're trying to answer, and why. Lots of times there's lots of puzzle pieces that fit together to answer complex questions. Yeah, I'll give a bit of an overview as well. Like someone said, just on I guess I'd say current trends in the industry or like in water resources in general. Happy to answer any questions that people might have in terms of like how like you as young professionals kind of fit into that and like how some of that works. And some, I don't know, thoughts, I guess, just on vision of what's to come. There's lots of very interesting things going on, and it's always just a matter of kind of people learning from the old and keeping up with the new, basically, because there's certainly value in both, and kind of need to at all times transition. But with that, I'll kind of walk through the slides. So that was okay. So as Dr. Rizzavi said, I'm Ross Phillips. I'm a hydrologist and water resource engineer. I sit here in Saskatoon. The work that I do is generally in Western and Northern Canada. So a lot of work in Saskatchewan, some in Manitoba, lots in the Northwest Territories, and a bit in Yukon. I do also work in Alberta as well, and I'm just kind of in the process of registering there right now. But I've been working now for 15 years. It doesn't seem that like it's been that long, but numbers don't lie. They're very objective. Um, I graduated in 2008, I guess, from the University of Regina, from environmental systems engineering. And then in 2010 from U of S with a master's of hydrology or through geography and planning at that time, but have an engineering background and just the way that things were structured at that time, the type of hydrology that I wanted to be working on was through I guess arts and science.
That was the strongest team at the time.
Yeah, well, and I mean, things are always changing a little bit. And there's always been some distribution of like hydrological sciences in arts and science and some in engineering. But yeah, so I mean that's where I fit. I'd say my research itself was a lot of focus on remote sensing, like monitoring of different like field-based monitoring of a lot of different hydrological parameters, and a lot connected to remote sensing, or the ground truthing of remote sensing and measuring storage distributed at scale through a catchment in northern Canada, and tying that to basically the expansion contraction of the connectivity of the drainage network, and change in runoff response. But my experience, so I guess that's my kind of academic background. In practice, I've done, say, a portion of civil engineering to do with hydraulic structures. I haven't done quite as much about that lately. A lot of hydrological modeling. Early in my career, I did a fair bit of, I'd say, hydrological monitoring work. I'd say it's as much as anything associated with my like extracurricular activities, than necessarily just academics. But I like outside of work, I used to race canoes a lot. I've done a lot of things in very like remote places. So it always was lots of fun to fit in time to go do helicopter-based trips somewhere far north, and you go collect measurements and then come back and run models. But I don't have as much opportunity to do that anymore, but more coordinating opportunities for people to do that. But it was nice while it lasted. So the group that I sit in at WSP, we're about 11 individuals in Saskatchewan. We're grouped in, like for water resource engineering professionals, we're grouped in with about 60 in Saskatchewan, Alberta, and the Northwest Territories. Kind of adjacent, so that's for water resource engineering specifically. So sort of like surface water physics, like hydrology, hydraulics. I guess like hydrotechnical engineering and like civil engineering to do with hydraulic structure design. Adjacent to that, we have sort of roughly equal sized groups that are dealing with hydrogeology and surface water quality. And then obviously there's shades of gray between, like, depending on the person, the specific person, their background, their interests, so on and so forth. That's just in the prairies and north. So we have, I'd say, similar side, similar, I'd say, like capacity and expertise, and like British Columbia, and on British Columbia, Ontario, Quebec, and the Maritimes. So this is kind of like a quick snapshot, just very local, kind of what we're in terms of scale. So you can see it's there's a lot of people. It presents like a lot of opportunities to work, like work with lots of other interested people. It's, I'd say, fairly diverse. There's people from all over, but generally sitting in Saskatoon, Calgary, Edmonton, or Yellowknife, where that's kind of where we have. And then with a few exceptions, we have a handful of people that, like we have one colleague who lives in Moose Jaw, and his family is there, and he's quite established, and so he's continued to live in Moose Jaw. I think we have one in Regina, but generally speaking, focused in those offices.
Choice Curtis?
Yeah, exactly. Moose Jaw's Curtis, and there's actually a couple people in Lethbridge too, working mostly with irrigation. So this is just to kind of give a bit of an outline of numbers. So these are numbers as a whole, just for WSP. And so in Saskatchewan, the 230, that'll also include sort of all sorts of other engineers, scientists. Generally, it's engineers and scientists, and some other, I guess, consultants, but and some support staff. But yeah, so Saskatchewan, Manitoba, there's, say, fewer than Alberta, British Columbia, and other jurisdictions, but still a pretty strong presence, particularly relative to kind of broader numbers in the industry. And also, I would say the 11 or 12 water resource engineers we have, as like out of a total portion of 230, is a big, it's a big piece of the pie. So there's definitely a critical mass locally. And then, as someone said, WSP as a whole, and so Golder, or like my experience goes back to when I was still with Golder. At that time, we were, I think, 7,500 people around the globe, and still like with a presence in Europe and Africa and Australia a lot too, Central and South America. But WSP is, I think, it's approaching 75,000 people around the world. So there's whole, I don't know, galaxies within WSP that I don't even begin to like fully fathom. But the important thing is just to know that there's a lot of opportunity within WSP for moving around, and lots of projects really distributed around the globe.
Canadian.
It is, yeah. And so it's headquartered in Montreal. But there's it's Canadian owned, but there's different companies kind of headquartered in different countries, like in part for like operational and tax reasons. And then kind of part of the broader WSP. So and functionally in terms of like whether or not you can work with other people doesn't really make a difference. Or like we have lots of people that are working. Like we have one senior hydrologist, 𝗪𝘂𝗿𝗦𝗂𝗃, who does a lot of work in Chile and Southern America. And have lots of people from New Zealand that contribute on some of our projects, and so yeah, it's different companies, but it's really all part of the same pod. So I'll kind of walk through a few projects. So maybe before I do that, just for general experience, so the scope of like the group that I am part of, like I said, it's mostly water physics, and that's obviously very general. But it includes hydrology, hydrological modeling, kind of like big scale physics of how much water shows up where, when, hydraulics, so lots to do with flood mapping, flood hazards, dam breach and inundation studies. So one-dimensional hydraulic modeling, two-dimensional hydraulic modeling for a lot of flood studies. Also, like computational fluid dynamics, like CFD modeling. Often to do with dams or specific structures. I'd say another big portion is like mine water management. So management and like containment, routing, treatment of water with mines. And so I've done a lot of that work, particularly to do with uranium mines, or ones that are like more regulated and there's more concern or risk and concern, and also effort, I guess, put into doing it right. We also do a lot of work with dams, irrigation, or like distribution of water for irrigation, and then a lot to do with environmental impact assessment, which we'll kind of get into in time. And I guess the for hydrology, or like for the hydrological modeling we're doing, generally it's in support of in some cases like peak flow potential studies, or like basically concerned about peak flows. Sometimes it's concerned with environmental impact assessment. Sometimes it's water supply, like over long periods of time, and sort of building out a case for whether or not there's sufficient water in a certain location to support whatever activity. But yeah, kind of crosses the full gamut. And then we'll say too, and I have a slide at the end, but my focus and the focus of the presentation is mostly on water kind of free out in the world, as opposed to like water treatment, or like water treatment, wastewater treatment, and that's kind of like a whole other and municipal distribution, that sort of thing, kind of whole other world. But have the privilege of being able to specialize and focus in on a few things. Yeah, so I threw together a couple examples here that I'll kind of talk through for hydrological modeling for water security, as well as some of the work I've been involved in and kind of ongoing for environmental effects assessment. like I said, I'll give like a broad overview and also I just have like a few slides for each, usually just maps. And so there'll be a lot of but what I'll try and go through is like the questions that we're trying to solve, the tools we're using just in a general sense, and kind of where the information goes. And then if anyone has questions, feel free to interrupt too, if you have questions with any of the projects. But also, I just kind of picked out of my hat like basin scale hydrological modeling and environmental effects assessment. But if you guys are interested in anything, any of the other topics that I mentioned, I'm happy to go through them too. So this first one is a project that I've been working on for the last few years, and I feel like we've reached a certain milestone. But in general, it's assessing water availability for power generation projects and specifically for small modular reactors or like nuclear power generating facilities. And so nuclear power generating facilities can use a variety of different cooling technologies, some of which require water. So you can use once-through cooling, where you basically pass water through a condenser and it cools down the generating facilities within the reactor, and then you discharge that water back to the receiving environment. So it's once through, it's just passing through in a cooling loop. The other technology that requires water is our wet cooling towers. And so those towers rely on evaporation really within the plant itself to cool down. And so those are ones that you could see having like a water vapor plume. Once through cooling, the first one, it doesn't really have any direct water consumption. However, when you discharge hot water to the receiving environment or like to the environment, you do change the temperature dynamic in the receiving water body, and that can lead to indirect consumption of water. So from the perspective of like a regulator or someone managing how much water is available for everyone, there is still some loss from that. And so, but more from an indirect consumption, because the actual plant just withdraws or diverts and returns generally, but the losses come in the receiving environment. For a wet cooling tower, basically there's a withdrawal and a consumption from the surface water environment because it's being evaporated. It's not lost from the water cycle. Like, I mean, it's kind of going up into the clouds, it'll fall down somewhere else, but it's being lost from that location. So from a water management perspective, it's a consumption, it's a use. There are other cooling technologies, like dry cooling towers, or that rely more on like a coolant, like a glycol or something like that. Or even some that are like a hybrid between, but just I guess for the purposes of conversation, the two that really require water are once through cooling and wet cooling towers. Once through cooling, it's uncertain or like it's complicated to say exactly how much water is being used. However, the magnitude of use is less than wet cooling towers, and then wet cooling towers require a lot of water. And so we were tasked with understanding how much water would be used for once through cooling. There's a lot of benefits to once through cooling. It's and with any technology, there's trade-offs, but relatively speaking, it's inexpensive. It requires less infrastructure. There is a high operating cost because you're pumping a lot. But from a maintenance perspective and from a capital cost perspective, it's competitive. So big picture, it makes sense. Or there can be a case for it.
Could you give us an estimate of the amount of water you might need for a single cooling system?
And so for
nuclear power.
So the nuclear power plant that we're kind of interested in this case was about 600 megawatt equivalent. So that's about the same size as the Queen Elizabeth power plant on the side, like near Saskatoon. That one is a once-through cooling, but a natural gas power plant. And so in this assessment, we're looking at needing like a diversion and return system of about 27 cubic meters per second. And so it's a big pumping array. And it's but the magnitude of the water use is like I said, much less.
But just for context, South Saskatchewan River, how much water? 250 cubic meters per second. So that's like 1/10 of that. 10%.
Yeah. And I mean, were it it would mean that you would be like pumping that amount of water kind of direct through. That said, it's if in an equilibrium state or in a constant loop, it shouldn't, like, it's not 27 away, it's 27 in and out. So it'd still be 10% like of the flow, but it wouldn't necessarily be 90%. Like it wouldn't be a 10% loss immediately downstream.
But yeah, I mean, the impact on the river temperature,
yes,
would be significant.
Yeah, and so
the species that they might suffer.
Exactly, and so for that reason, generally in a modern environment, we don't use once-through cooling on a river or like on a riverine water body. It is different and different dynamic in a reservoir or a lake. And then the scale of the like a wet cooling tower consumption is about 0.5 cubic meters per second for the same size of power plant. So we went through a big process to identify sites that could potentially be suitable. Our clients in this case was SaskPower, so the provincial power utility. We did look at water courses, the South Saskatchewan, North Saskatchewan, and the main stem of the Saskatchewan rivers, but those were screened out, in part because of the reasons that you say. And ultimately, the thermal plume, like the plume from the heat, would occupy basically too much of the river and change the temperature dynamic of the river too much, and particularly during like warm periods. There'd also be some operational risk, like as a cooling technology during like really hot periods. So as you can appreciate, especially with the South Saskatchewan, it's shallow, it's clear. There are periods of the year in August, July, August, where the water temperature is much higher than it is in winter. And really the change in temperature, or like the delta T, is what you need for cooling. So winter, it's nice and cool. I mean, flows are low in the winter, but nice and cool in the summer. It'd be more prone to having water temperatures too high, and that can be problematic for operations. But so this figure kind of puts together all the pieces we did in a general sense to ultimately answer the question of water availability and identifying risks. So we did a climate change assessment specific to the watersheds we're interested in. And so really developing like daily time series data, downscaled and bias corrected to, at that time we were using multiple points in the watersheds rather than like a full gridded data set, but really to project what future climate conditions might look like. We did basin scale hydrological modeling. In this case, it was primarily done with HSPF, based on, I guess, experience that we had with like a calibrated kind of good performing model, particularly for the South Saskatchewan River. In the two watersheds we became more focused on were the South Saskatchewan River watershed, feeding Diefenbaker Lake, and really Diefenbaker Lake it being the I guess the location we'd be interested in. as well as the reservoirs located in the Souris River Basin, so in the southeast of Saskatchewan. There's a few different reasons there, and there was say in parallel to this, a general siting study that was done that tried to integrate multiple different criteria and really like inputs considerations into where the best site was. But and I won't go into that in detail, but it's kind of ranging all the way from like where consumers are for power, where a good water source is, where transmission lines are. And so the cost associated with like patching a new facility into the transmission network, but also things like transportation infrastructure, particularly for transporting like really heavy loads. So also integrating information about rail lines, like heavy haul highways, but and then seismic activity is another. But usually things are oriented around like environmental performance or technical operational requirements or cost. And I guess also like social, like how people engage with it. So then that hydroclimate modeling study fed into a reservoir simulation modeling study. So this was developed and sort of tailored in GoldSim, which is a systems dynamics modeling platform. And really, what we did there was like take the basin scale hydrological modeling as inputs, combine that with variations in water use by others. So integrated information about current and future irrigation plans, current and future use by municipalities. Both of the systems I described or I mentioned are relatively complex, or like there's water management activities ongoing. So like Diefenbaker has diversions through the Qu'Appelle River system to support the municipal requirements of Regina, Moose Jaw, other communities and First Nations further downstream, potash mines as well. There's also diversions to the Saskatoon Southeast water supply, but to the south of Saskatoon, there's a canal system that goes from Lake Diefenbaker really all the way to Lanigan, but supplying irrigation systems and potash mines. And then there's planned irrigation. So I'm sure many of you will be familiar with like the West Side irrigation project and I guess different phases of that. So we integrated that into the reservoir simulation modeling as well as the operating rules for the dam. So I guess just a little bit on the modeling side there. We, in developing sort of a tailored model to the Lake Diefenbaker, for example, we did sort of follow a many stage approach to try and control for things we didn't know or like control for variables. And so basically to start with, just used a historic model or like historic time series data with where we knew the operating rules and we knew actually first there was no operating rules, measured inflows, measured outflows, just to make sure that we had all of the components of the water balance accounted for, and particularly that we had a good representation of evaporation. Then next step was measured inflows, measured outflows, but adding in the water management rules, or like the operating rules, to make sure that we had a decent representation of how people, or like how, in this case, Water Security Agency and the operators were managing the reservoir. And then after that, we actually proceeded with the actual calibration of the model and performance testing. And then so I guess the top kind of blue arc really captures what's going on in the reservoir. On the bottom arc, we did is more to answer the question of how much water would we lose to evaporation. And so the water field studies here, we had it's a fairly, I found it very interesting, but fairly intense monitoring program. So we deployed thermistor strings throughout the different reservoirs that we're looking at I think 6 different locations. And so we had temperature measurements, temperature conductivity measurements distributed throughout the water column. And those ran on like a 30-second time interval over a few years. As well as ADCPs, or acoustic Doppler current profilers, to measure velocities, like at different strata through the water column. And then a lot of other manual measurements just associated with the density and cycling of the water, but physical chemical profiles at all those different locations roughly monthly, and then water chemistry samples, but mostly geared around like total dissolved solids and like major ions, but really like in terms of like how dense the water was, more than anything, and total suspended solids, or TSS too. So that all that data fed into, and then we had water level distributed at different locations in the water bodies too, just to see if we could measure any satiating, or basically the movement of water from wind. That fed into a hydrodynamic model for each water body. And so the hydrodynamic models were developed in Mike software, Mike 3FM, and basically calibrated. It's a 3-dimensional dynamic model for the water body itself, calibrated based on that existing conditions information, as well as in the case of Boundary Reservoir, the existing coal plant. So the existing coal plant also has a once-through cooling system, and so it discharges a lot of heat into Boundary Reservoir at present. So we incorporated that as well.
Here, what you're describing is so huge in scope. All the from climate change assessment, hydrologic modeling, reservoir, future water availability assessment, hydrodynamic modeling. How many people were involved in it?
That's a good question. Yeah, and it's not just me.
I mean, this is just so huge.
Yeah, so I'd probably say 30.
30.
Like in various roles and various capacities. But generally I'd say for each modeling study there's probably 2 or 3.
And did you say you looked at the entire Saskatchewan River Basin feeding into South Sask?
For the modeling, yes.
Wow. And we ask what you might have already said. What model you used for?
For that, it was HSPF.
HSPF.
For the basin scale hydrological modeling, and then the reservoir modeling itself was in GoldSim.
A reservoir model, you mean? What reservoirs exactly you modeled?
So there's 2 different models. So one for the South Saskatchewan River Basin. So in that one, really just Lake Diefenbaker for the reservoir, and then really the watershed upstream of Lake Diefenbaker, but then Lake Diefenbaker. For the Souris River Basin, it's a little bit more complicated. And without going into too much detail, basically there's Boundary Reservoir, Rafferty Reservoir, which are very close together, and another reservoir called Grant Devine, and formerly Alameda Reservoir, that are all in the Souris River Basin. The Boundary Dam Reservoir and Rafferty Reservoir are located so close that you can send water from Boundary to Rafferty via canal system, and you can pump water from Rafferty to Boundary via pumping system. Rafferty Reservoir was constructed in part to have additional storage for Boundary Reservoir for the power generating there. things have changed a little bit, like in terms of where where Estevan, and this is all right near the city of Estevan. And so historically, Estevan had gotten their water from Boundary Dam Reservoir. That's recently changed, and so they get it from Rafferty. The point, and then I guess the third variable in that is that for the Souris River Basin, Canada has obligations under the International Joint Commission for the Souris River Basin, whereby we need to send a certain amount of water each year to our neighbors to the south. And there's three stems, like three key tributaries that come together as the Souris River before it gets to Sherwood Crossing, which is like the point where that's like that commitment is evaluated. And so Grand Divine Reservoir is located, I should have brought a map, but it's located on the Moose Mountain Creek. Boundary Reservoir is located on Long Creek, and Rafferty Reservoir is located on the upper Souris River, the main stem of the Souris River. So for that model, for the Souris River Basin, we needed to integrate all three so that we could account for transfers between Rafferty and Boundary, like both for flood protection or flood mitigation, as well as like operational water requirements for the power plant. And then we had to also include operating rules for all three so that for flooding and flood mitigation and apportionment requirements. But yeah, so it is a very complex, but so just back to the hydrodynamic modeling study. So that one specifically, in the end, gave us a representation of just how much evaporation would be used. And we had a bunch of different scenarios, like looking at different periods in the future, like kind of early century, mid-century, late century, as well as really zooming in on droughts and what that would mean. We also looked at I guess the relative difference of if you put a power plant on Boundary Reservoir, if you put a power plant on Rafferty Reservoir, and sort of what the differences would look like there.
And could you just restate when this project started? Like, when did you just start all of this research into this?
So 2023.
Okay.
Is the mic on by the way?
Yep, got it.
So yeah, I think we will have started this work in earnest in 2023. We installed the general work, like I was saying, looking at all the water bodies. At that time, I was looking at all water bodies below 54 degrees latitude in Saskatchewan. That started in 2022. And then I'd say we've kind of reached the end of the arc here, probably around Christmas. But and there's still work ongoing, and there will be more refinement. But I think in terms of this milestone, but yeah, then ultimately you're able to compare what cooling technologies are appropriate for different locations. And in general, the main takeaways I'd say are that Lake Diefenbaker has quite a bit of water, and so there's less constraint on. And I should caveat that all of this is like sort of proposed. It's all subject to like approval of water licensing and so on. But yeah, Lake Diefenbaker in general is less prone to constraints, and for a power plant of this size, would be able to accommodate either once through cooling or wet cooling towers, if that was I don't know, attractive for other reasons. Then in the southeast, though, wet cooling towers just consume too much water, and that there would be constraints on really whether or not that could be applied. I think it could be applied on Rafferty Reservoir, but would need to be, I guess, reviewed whether or not the like the use of water for that reason was acceptable, but just from a strict, is there enough water, like to not have like risk of not having enough? I think that's fair. And then, but Boundary Dam Reservoir and the watershed that support it really could only use once through cooling technology, just because there's only so much, and it would require you'd be functionally running it off of Rafferty Reservoir. If you used a different, you'd just be pumping from Rafferty Reservoir to Boundary. So yeah, that's kind of like in a nutshell. So ultimately, the importance of this work is for like siting of nuclear facilities, and so as you can appreciate, there's a lot of regulatory requirements and importance put on like on various different stages for nuclear development. So in general, those are sort of siting, basically deciding where to put facilities. Impact assessment, which is yet to come. This isn't directly part of an impact assessment, but in future could be. And then the other stage is a license to prepare a site. So all those, and they're kind of strictly mandated, kind of governed by certain processes. But so this is all just to support like a educated, like information supported decision on where to put what type of facility. I'll skip to the next. So this one, this may be a little bit more, I don't know, not simple, but just a little bit more straightforward. So I don't have it called out on the map here, but kind of right where my cursor is where the 𝗪𝘂𝗿 mine complex is. And so the 𝗪𝘂 mine operated from, I think, the 1970s through to the late 90s. At that time was the largest lead mine in the world. The mining company that operated it went bankrupt, disappeared, and it is now the responsibility of the federal government. And so WSP is working with the government of Canada and a number of other consultants as well, like many people, to reclaim and remediate the site. And so as part of the work, WSP is doing water quality modeling for the receiving environment. So specifically this Anvil Creek that you can see there. And also for the 𝗪𝘂𝗿 River itself. And so the Anvil Creek watershed, as well as the Van-Gorder Creek watershed, is where there's kind of this relic contamination that's being remediated. And then the 𝗪𝘂𝗿 River is basically a very important, quite large watershed and river, important to the people that live there, First Nations, local people. And so ultimately there was a need for future flow information for the 𝗪𝘂𝗿 River. And so we developed a hydrological model in the Raven modeling platform with ℎ𝑏𝑣𝑒𝐶, and basically used a multi-point. You want to ask a question?
I mean, just interesting. So you do Raven as well. So
Yeah.
I mean, because we've been talking about different types of models. This information very useful. That's why I'm just emphasizing. So HSBF was the other model for this different project. This is Raven now.
Yep.
So you're working with James Craig then directly, or?
We have correspondence, and like there's like also I'd say within WSP there's lots of people working with Raven, and there's certainly some that have a lot of direct correspondence with Dr. Craig, but I'd say we have kind of a similar approach to really any model. And so it's a good topic, and really, and we can go on, I don't know, like, we can go into quite depth about like different models and so on, but my general philosophy is the Really, like any tool can be the right tool if it's a question. And so it's important to, so I guess the rationale for the HSPF model. So HSPF is a like it's basically a distributed hydrological model that has been used a lot, particularly in Alberta, in the last 25 years, really 25 years. And specifically for the South Saskatchewan River Basin, we sort of knew it to be functioning quite well already, specifically for water supply. And so sort of continued to apply and like build upon that. Now, like the models like through Raven, I mean, and you can kind of go through the full scope, but like a model like Raven or the models within Raven, I guess, present some opportunities for just efficiency and calibration, efficiency and like workflows of like developing the model. And certainly suited this environment too.
And by the way, here we are building some strong capacity in Raven modeling as in USask, because Raven now is equipped with water management as well. So you can have like gold sim type reservoir operation and stuff, hydropower directly built in with optimization for water operation. So it's quite a powerful platform, and we're doing a lot of research with James Craig. And
I'm really interested in that specifically. Like I saw in the most recent publication or like kind of version publication that there was that was built in, and we have one project in the Northwest Territories where I'm hoping that we can do the same. But I'd be very interested in knowing exactly what that looks like. Because a lot of the limitations of strict hydrology models is, and I'll kind of get to it in the next one, like what happens when you get to the reservoir. And some are better than others in terms of like the detail that they can go into, but some are very focused on the big picture.
I can say with confidence that Raven is going to be the very first modeling platform globally that can accommodate both hydrology and water management.
Yeah, that's great. Or like that's I don't know.
Good for James, but
well, I mean, great for everyone. Like, I mean, it's and it's I don't know. Thanks be to Dr. Craig and everyone else who's worked on it for developing those tools. But like as a practitioner, like that'll be very powerful for us to use to kind of get better information. But yes, so we for this model specifically though, we used HPVC within Raven. It calibrated very well. And ultimately we were focused on generating flows really throughout both existing conditions flows, but till 2100 to support that water quality modeling. So the next one, so this is work that we've done in northern Saskatchewan for an environmental impact assessment. So the next gen 𝗪𝘂𝗏 mine, or I guess operation, is a proposed uranium mine and mill facility in northwestern Saskatchewan. It's about 200 kilometers north of La Vache and about 150 kilometers east of Fort McMurray. It's a fairly remote location. It's on the headwaters of the Clearwater River. And so for this particular question, I will have been looking at basically leading the hydrology component of the environmental impact assessment. As you can appreciate, there's many different disciplines that go into an environmental assessment. I guess key related ones will be like hydrogeology or like groundwater, as well as surface water quality, aquatic ecosystems, fish habitat and health, and environmental risk assessment, but kind of working down the line. You can see that just from the map, the landscape is very lake dominated. And so the other aspect of the landscape there is it's highly permeable, overburden. There's not really very much soil. It's mostly just sand with like a thin veneer of like organic soils and maybe some caribou moss, Labrador tea, black spruce, but it's generally speaking, the landscape is like rolling with like sand and boulders. Um, and so from a hydrology perspective, um, and just like how the I guess the physical environment works. Generally water, I mean, water falls, some is intercepted to the canopy. Um, Otherwise, what hits the ground infiltrates immediately. It's then sort of stored or it's routed subsurface as really runoff, like through shallow pathways, but it's really slowed down. Then it's makes its way to a lake. There's level pool routing there, and then sort of enters the stream channel network or drainage network at that point. There isn't very much in the way of small water courses, like little creeks or anything like that. It's really once the water is concentrated in lakes. And so in order to, and then I guess the other priorities of the project are that the water quality is very important. Kind of, I'd say even more important than the hydrology, even though I really like the hydrology. And that we kind of need to be able to assess, sort of tailor our model to assess the impacts of the mining operation. So this model we actually built in GoldSim, but built out a distributed hydrological model within GoldSim. And so sort of all the processes I just mentioned, and many that most really that you would see in a hydrological model, like a, I don't know, off-the-shelf hydrological model were built in. So we had basically storage reservoirs distributed through like the terrestrial environment, so storage um, in the vegetated canopy, kind of available to either overflow or evaporate or evapotranspirate. Storage at surface, albeit it's pretty low in most of the watersheds. Storage in subsurface, like soil storage, and really like sort of base flow routing through that storage reservoir, and then storage distributed through the lake networks. And so I wanted to include this example too, just to show that there are lots of instances too with hydrological modeling where there can be a rationale for maybe taking parts like of a routine hydrology model, and I mean it's very promising if some of the tools are kind of catching up so that you can build in more functionality into one. But I guess in this case too, once we're done with the hydrology component or the surface water quantity, basically then we hand it off to the water quality teams who then integrate the functionality associated with water quality processes. I guess other interesting things with this one from a modeling perspective, we divided up the different the lakes into kind of different basins. And so Patterson Lake here was divided up into 1, 2, 3 basins, kind of based on the morphometry of the lake. And then Forest Lake, this one, was divided up into one basin here, and then a big basin down at the bottom. And like within a daily time step, it would iterate and basically decide if water would seiche back and forth between the different reservoirs, or different basins, which was important for the water quality, in part because the discharges from treated effluent and treated sewage would just be to this one basin, and then just understanding if it moved one way or the other. Okay. So the next slides I'll kind of shift away just from just the hydrology perspective, and I'll kind of give a little bit bigger picture of a few projects that I've worked on. So WSP did a lot of work at the 𝗪𝘂𝗿 mine. It's a diamond mine in Northwest Territories that's currently being closed. So in the general scopes for the mine closure include everything from like covers to um, different sort of remedial infrastructure to basically stabilize and revegetate the disturbed area and really return it to the receiving environment. Now, personally, my primary role in this was designing intakes. So like designing intakes for very big siphons that would be used to fill up the ponds, or sorry, the old pits. So basically sizing screens for the end of a pipe, large fish screens so that you don't impinge or entrain fish. So Giant Mine, this is another gigantic project that WSP has been working a lot on. In general, again for Giant, it's a relic mine that's now in the hands of the federal government to reclaim. It's an old gold mine. The big challenge with Giant is that there's a lot of tailings on surface. The other is arsenic. So there's a lot of arsenic that's being stored underground that in the past has been cold and sort of stable because of that being cold. But as things warm up, that can change. And so in general, the work at Giant is to stabilize conditions and really keep them from getting any worse. Now, I won't go into too much detail. So I guess my experience with Giant, so my research was on Baker Creek, the Baker Creek Research Basin, which is running through the mine site, kind of like this. But so I have a close attachment to the creek itself, just from kind of having lived there and done a bunch of research on it. I did do a dye tracer study 2 years ago there. And so another portion of the work that I've done is a lot of rhodamine dye tracer studies. So basically putting fluorescent dye into water bodies and evaluating I guess the migration of the plume, and in this case, it was looking at there's an instance where Baker Creek runs adjacent to an open pit. The creek will be, I think it's about 35 meters super elevated above the bottom of the pit, and on the one side is the rock face. Ultimately, the historic channel will have gone through where the pit is now. And in order to mine that in, I don't know, 50 years ago, something like that, the company rerouted the river away from where the gold was, and basically dug a big pit there. And then now there's been some instances where water has shown up in the bottom of that pit and also in the underground mine workings, kind of down below the pit. But without like a clear overflow, like from the river. And so there is a question of whether or not there could be water coming from the river into the pit, into the underground. And so in that instance, we used rhodamine, which is a fluorescent dye, and deployed instrumentation along the creek, as well as the bottom of the pit, and then released flood releases of dye. And then based on like a two-dimensional Gaussian plume model, like fit that to the information that we were able to like collect from the monitoring instrumentation. It was really interesting because we did it 3 times and we observed 3 times like pulses in the bottom of the pit, all with the same like time delay and with the same concentration. And so we were able to, based on our plume model, or like our dispersion model, identify like roughly where on the creek, basically on the logical assumption that if the concentration arriving at the bottom of the pit could only be equal to or less than the concentration at that point, like at whatever point it left in the creek. And so we're able to identify the like specific location. It's about 50 meters downstream of where we released the dye. And then we're able to kind of trace back and find that there had been a liner installed in the early 2000s, and it was right near where the liner ended, where the water was getting out. But okay, I also do a lot of work in northern Saskatchewan at the existing uranium mines. So this is at McLean Lake in northern Saskatchewan. So it's a former mine currently operating as a uranium mill. And so I guess personal involvement here, I've done a lot of erosion protection design for the ramp kind of going down into the in-pit tailings facility. But other colleagues of mine have done a lot more. Okay, another site where I've done a lot of work is 𝗪𝗂𝗏𝗃. So this is near Bethune, Saskatchewan, so on the way to Regina. What you can see here is the cooling pond, as well as the brine reclaim pond over here. And so my involvement has obviously been on the water side, but both in terms of the design of the cooling pond, the design of the baffles, and I guess establishing like operating criteria for like where they need to operate their water levels. So typically the information that goes into that is some hydrological modeling, albeit it's fairly simple. These are contained sites. It's not like a big watershed reporting to it. And so, I mean, there's a fairly conservative magnitude of design events, but it's like dealing with 300 millimeters in 24 hours, but from a very local watershed, like just pretty much the footprint of the pond. We also need to do assessment of wave action though, like wave setup, or I guess wind setup and wave run up for establishing freeboard conditions. And then something that we're currently providing support to 𝗪𝗂𝗏 on is, and we've provided additional support before, but to do with dam break and inundation studies and translating that into consequence classification for which defines kind of like how they certain design criteria for the dam structures and also how they can be operated. Okay, so yeah, and then I just wanted to have kind of a couple general slides at the end too to capture off some of the other sort of typical work that we do. So like I said, for hydraulics, flood studies is a big one. We do within Saskatchewan, we've done, I'd say probably 12 communities over the past 5 years. In Alberta, I don't even know how many more in Alberta. But
It's a good question. So flood studies, you do like floodplain mapping through 2D modeling?
Yeah, exactly. So generally it's two-dimensional hydraulic modeling, often using ℧RAS 2D now. I feel like since ℧RAS kind of gained two-dimensional functionality, it's sort of been the go-to for that kind of work. And it's I don't know, freely accessed, or it's free, so it makes it a lot easier for more people to use it. But yeah, so the general sequence with that is we do a lot of hydraulic surveys, so both topographic, bathymetric surveys, as well as getting information on like velocities and so on. So here, this is a river surveyor, like a Sontec M9 with a RTK, or like a real-time kinematic GPS on the top, completing the river surveys and then feeding into the the hydraulics or like hydraulic modeling, and then the mapping is a big component of it too. I guess one example study that I did recently for a flood hazard study was I did a economic trade-off analysis for the community of Lumsden, which was fun for me because that's where I grew up. But basically, the Lumsden is located in the Qu'Appelle River Valley. It is inherently flood prone, given its location. In the 1970s, there was a series of dike works or like flood control, flood mitigation works constructed through the town. They were improved in 1998 and finished in year 2000. But the Qu'Appelle River has a large sediment load. And so in the 1970s, well, I guess just to kind of, in general, things can change with design events. And so in the 1970s, things were constructed, or like the flood control works were constructed to a 500-year return period flood at that time. Over the operation of that channel, like basically the excavated channel cross section and the dikes, sediment is deposited through that reach and basically consumed some of the conveyance capacity of the channel. And also over the past, I guess, 40 years since the last revision of 45 years since the last revision of the flood flows, more information has become available. So the actual magnitude of the 500-year flood has changed. And so there's a question of basically knowing that you can no longer meet what's established as the 500-year flood. Basically, what do you do about it? Like, and so that study we looked at basically using a hydraulic model to establish what different options were to pass that 500-year flood, and really floods of various different magnitudes. Did costing of how much it would cost to construct those, and then in parallel to that, did an economic analysis of basically net present value of damages associated with each different flood. And so then we're able to establish curves of basically plotting the cost of like the cost to protect versus the cost of loss. And we're able to establish what options are actually economically efficient. Or so hydrology, this is kind of more of the same. This is an example here of an acoustic Doppler current profiler, a stationary one that we use, ADCP. It's a 𝗪𝘁𝗂𝗿, I think, on a 𝑤𝑖𝑒 float, but this will be associated with that SaskPower project that I was talking about. This will have been one of the instruments that was installed in measuring lake currents. Yeah, and then this one, it's just kind of a general introduction to the other side that I was mentioning about hydraulic structure design. So, pardon me. So I've been involved in a bunch, but everything from hydraulic structures like spillways, dams, I mean, culverts, bridges, involved in that too, for conveyance or cross drainage structures. Conveyance channels. So I've designed a number of different conveyance channels at mines, some in really remote locations where really the only equipment we had was a helicopter for construction. Flood mitigation works. Yeah, a lot of the work we do too is to do with like aquatic habitat. So a lot of fish passage design. Was involved in a project in the Northwest Territories where we designed basically spawning, call them baskets, but they were basically rock structures about the size of the room, but shaped like a basket with baffles in it, immediately downstream of a hydroelectric facility. And so basically fish swim up to the penstock or like where the water is coming out from the dam, and they want to continue to swim upstream, but they can't because of the dam. And they spawn by broadcasting, like they basically lay eggs into the fast water. And so the habitat that we developed was basically designed so that it would catch the eggs and be faced or surfaced with the appropriate like material that the eggs needed to hatch. And so, anyways, yeah, wetland design, especially in northern Alberta, where there's like reclamation of oil sands facilities. So this slide here, this was what I was kind of getting at earlier. So everything that I've talked about is really over on this free water side, and it's definitely been my focus. But I guess just for all of you, depending on kind of what interests you and what your background is, just know that there's a tremendous amount of like opportunity and need in the more the managed water kind of built environment system too. But yeah, and I guess that kind of feeds well into like the visions for industry. And so that's like a lot of information, I'm sure, for a lot of different projects. Not too much detail really on any one thing, but the hopefully what you can take away from that is that there are a lot of like complex and interesting things going on. Like water is very important for society and for I don't know, economic development in general. And so yeah, I think it's great that you're all interested in water and pursuing a career in water. And there's often opportunity at WSP. We're always looking for more people. Certainly encourage you to engage with us. That said, like it's generally just nice to see lots of people kind of pursuing that path, no matter where people work. And it's ultimately a really small community where we're often working together, whether it's different businesses or businesses with university or businesses with regulators and government or universities with government, or like it all kind of still remains like a small community within that. So and I think I guess the other visions for the industry, like I think we're currently like going through a lot of technological change, like just society in general. And like I think the new models that we're discussing are like a good example of it. But I mean, to me, it's a scaled out version of something that's been happening for quite some time already. Like 50 years ago, there wouldn't have been like a PC. And like 30 years ago, really would have been, I don't know, the first generation of people like really engaging with like spreadsheets and things like that on a day to day. And like kind of widespread application of hydrological models, kind of same sort of era, kind of like late or like mid to late 90s, and like progression they're on. And so I think the discussion we had before about like which model to use or like which technology, like I think it's important to like remind yourself that um it's always changing and it always will change. A lot of the underlying information or physics or things like that, it's not all that new. It's more just like how they're all packaged together and how the computing is done. But just to I don't know, have a clear mind and conscious like selection of whatever tool you're using. But it doesn't necessarily, one is not necessarily the only tool. And that you can have like a simple question it's acceptable to have big error bounds that you could use, I don't know, back of the napkin, like just hand math or something like that. But then could be that there's like a more complex question where the error tolerance is low. And I mean that maybe that one example that I spent some time on is a good one. Where so it took 30 people plus a lot of effort to get to like hopefully in the end like a digestible piece of information, but a lot of complexity within that. And so just appreciate that there's the full range of things. And then I guess the other like thing that's obviously rapidly developing now is AI and machine learning and so on. And I think the at least in the short term, I think even if we're using AI, it's the responsibility is still on the person to basically to own what the information that's being kind of put out. But
I was about to ask you about AI and your vision of it. Like, do you think 10 years from now we might have an AI-based Ross here teaching to us this, telling us what's happening in industry?
so yeah, the challenge I have with that, or like I think the big jump is you still need to communicate, like at least maybe this is kind of ventures into the philosophical a bit too, but like I think we have an economy because we have people. Like basically an economy is economy is society, and you can pick what word you put for it, but like it's the ways that we all kind of come together to create something that's bigger than ourselves. And I think like a big part of especially my role right now is explaining things to people, and like summarizing complex things, communicating them, and maybe we'll get to a point where AI is capable of doing that flawlessly. But I don't see it right now. And the I guess the nuance and the complexity of just like a real world interacting with people, I think there's is still a real need. I do see a lot of opportunity. Like I mean, particularly like Canada, we don't have that many people, and like we're always striving to get more people, and like it's always great when we do get more people, but really like when you kind of zoom out, like if we're say 40 million people now, I mean even if we were 50, that's like a big change. Ultimately, I think we'll still be in a position where we're limited by the number of people we have. And so I think things like AI, if that meant that the 40 million of us can be like ever more productive and kind of do more and more, then I think there's definitely room for that. But I feel like that's also kind of in line with some of the gains that we've seen over the past like 40 years with different tools.
Good. So, on that word of wisdom, we have about half an hour
Okay.
to go. Here is my suggestion. We take a break for 5 minutes or so. Everyone could stand up, go to washroom, get re-energized. If you need to get some water, that's just down the hall. There's a fountain here, and then we reconvene in about 5 minutes or so, and we'll go under 3:30 if we can stay longer.
Yeah.
Of course. Yeah.
Yeah.
Yeah. Okay. So at this point, please just join me. Okay. For giving this very comprehensive, great presentation.
Thank you. That was good timing too, because my computer ran out of. We could have plugged in and then. Yeah. 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 Yeah, no, we've been really lucky in the past few years been lucky overall, but to be able to work on really interesting things. Yeah, we have another project going on now that's on Great Slave Lake. That'll be similar in some ways to that one, which is very exciting. But yeah. This one is not It wasn't too ambiguous, actually.
But they can find people.
Well, and I feel like that's the real benefit. Yeah. And it can also create an environment where people can speak.
Yes, of course.
No,
No,
like for me,
it will be something
like
easy.
when I first started working,
Hopefully
we've
it's
changed
something
the
easy.
how we over time. Like when I first started working, we were organized like the Saskatoon office, and so basically I did a lot of things just locally, sort of, and I'd say a broader range of things. Even though I'm really interested in the hydrology component, I mean, there wasn't someone else who could do like hydraulic structure design, or someone else to go do the field work. And like as a individual, there's only so much work one person should be doing. And so it's been very nice, even from a personal perspective too, if you're trying to strive for those bigger, like big ideas, big complex things, you need to be able to access a broader group of people. And if it's opened up like to broader geography and you can engage with lots of people, it really means that you can do bigger, more interesting things. And two, like it's nice to have other people's ideas or like exchange. And I feel like the technology we have now makes it really accessible to like be working with people in Montreal.
Like that's the fun part of it, to collaborate with others.
Yeah.
Travel. I mean that's for me.
Yeah.
Just talking to you is fun.
Yeah.
I just see what's happening here, there, collaborate.
Yeah. No, for sure.
By the way, if you need to get water or washer on the hall, yeah, just leave it here. You're gonna need it again.
Yeah, so all I did was.
The project's ongoing right now, so I would say that there's probably way more than I know, like just based on the focus of my work. But I do. There have been folks, like colleagues that have worked in Guinea, Ghana, Côte d'Ivoire, Zambia, really all over. So like I think there are many projects. I'd say just that me personally, I haven't been as involved in them. Was there a specific country, Richard, that or is it more just general?
So I was asking a general question, but I'm based in South Sudan. I'm in Juba.
South Sudan? Okay. Yeah, so, and like I showed on the map there at the beginning, just with I don't know, where everyone is, like where there are WSP employees. I'm not sure. I was more familiar when I was still working for 𝗪𝘁𝗲, like where exactly all the offices were. But and at that time there was a big presence in South Africa and Ghana. South Africa, Ghana, and Guinea, I think. But it'd be something to look into. There'd be sort of far more information than I personally am aware of right now. And then for AI, yes, like we're currently engaged in projects as well where we're looking at like using machine learning and so on, especially to do with remote sensing products, and improving I mean, both the structure of models and even just the way that we're doing modeling. But and really what information gets fed into it at real time. But specifically with I mean, a lot of things to do with soil moisture, snowpack, snow cover, but yeah, a lot of AI for processing remote sensing data as it relates to hydrological models.
As your follow-up question on the AI work, I just wonder who funds your AI type activities?
Some of it's internal.
Uh-huh.
So just corporate research and development processes. Some also like from federal government projects. So I know there was one federal government project which we were not successful on, but we bid on. That was basically to develop AI and machine learning approaches for regional flood mapping or flood mapping at a regional scale. So much of the flood mapping that we do, or that at least in Canada is sort of mandated and required, is what we would call development of like engineered flood maps that are very specific to like communities. And maybe some jurisdictions like Alberta extend for like full river reaches. That's quite expensive. In Saskatchewan, we've typically taken the approach of looking at like basically where there's a lot of people, or like in say a city like Saskatoon, or even something like Weyburn or Estevan, and defining the boundary of the flood mapping scope to basically where there's a lot of development, a lot of risk. That project was looking at basically the spaces in between, like how could we use AI to have a far more economical, like a cheaper approach than just the amount of effort it takes for the detailed flood mapping projects. Does that answer your question, Richard?
Yes, it does. Thank you.
Other questions?
Yeah, I have a question.
Okay, Klima, go ahead.
Thank you for the presentation. You know that we are doing this master's, it's the professional master's. But can you give, in your experience, that how can we improve ourselves for water-related career more?
Like a kind of in addition to, or just,
Yeah.
well, I think like I think obviously you guys are getting a strong technical education and kind of, I don't know, in the right place for that. I think like a big part of, like I said, a big part of the job in the workplace is communication. So kind of encourage you through your studies to take opportunities wherever you can for public speaking or engaging with like other team members, and like really taking that seriously. Just in the work environment, much of what we're ever doing is collaborating. And then I feel like I guess other things for the modern work environment, I'd say being able to structure time where you can multitask, but also structure time where you can actually focus, with I don't know, notifications and texts and screens and all that. There's no shortage of things for, and just with friends, family, all the good stuff. There's no shortage of distractions. But then ultimately in any like any job, and really no matter kind of where you're working for, you do need to have some time where you can focus, and actually like produce, like whether it's create, whether it's doing the modeling, like writing code, or like actually like troubleshooting, something like that, or writing or making presentations, something like that. I find increasingly need to just be disciplined, I guess. And it's different for each person, but I feel like generally having some time where you can really focus, and however that works for you as a person. And then also having the time that you need to, I don't know, multitask and keep a bunch of different things going. But I think if you only ever, there's a risk in the current context, if you're always just multitasking, then I think sometimes you don't have the chance to kind of go to the depth that you need to as like an expert.
Thank you.
Who is online? Dorothy, go ahead.
Thank you, Ross, for your presentation. Now I understand why Dr. Owoveh was so excited about you coming in today. He was all over the place. So now it all makes sense. Thank you for your presentation. Now I would ask you, what are the skills like you would tell me, for example, who's looking into stepping into the industry, what are the core skills you would suggest me? Say, oh, wow, you must have this and this and that specifically. If you can narrow that down for me, please. Because it seems like the job descriptions they vary significantly from the type of models they want you to know and the even background that you must have. So can you please narrow down some core skills that are required for someone to step into the industry? That would be one question. But the second aspect of my question is, according to your experience, how has modelers changed over time? Like from when you started to now, what was a water modeler look like 10, 15 years ago, and what is a water modeler looking like nowadays from your 15 years span?
Yeah. So maybe I'll answer the second question first. Like I don't know if I have like a strict vision of like water specifically like water modeler looks like. Um I think to me the successful people like the successful individuals that I've been working with have, I'd say, exhibit a lot of the same traits, kind of like moving along, like both the people interacted with maybe 15, 20 years ago with those I'm interacting with now. I mean, I think the work environment, at least the work environment I've been privileged to be in, was pretty diverse to begin with. I think it's even more diverse now. And so I wouldn't say like 20 years ago or something that someone like looked like a certain type of person, and it's different now. I think just the where been privileged to be, it's always been pretty diverse and inclusive. I think some of the concepts we talked about today, like basically having the creativity to select, like to choose which gear you need, is a really useful trait. And I think it's something for everyone to kind of reflect on with any question. Like to basically fit, and if I read on a resume that someone knew 10 different models, but then put in a line said, I've worked with to summarize, but like I've worked with enough models to be able to differentiate between what tool is necessary for the job. Like that line would catch my eye. And so I think like kind of just to be conscious and discerning in and like I mean exhibiting that you can have a plan and deviate from the plan if you need to, is like a really attractive thing to see in a colleague too. The ability to work together on teams. I mean, I've I've interacted with a lot of people that are brilliant, like I don't know, sort of next level brilliant, but sometimes sort of struggled engaging with other people. So I think to the extent that any of us can, like doing what you can to engage with other people is like very helpful.
By the way, so is computer programming or Python
Yeah,
helpful?
it
A
is.
lot helpful or
No, it is. And for all the platitudes about like the right tool for the right job, um, proficiency in R, Python, MATLAB to a degree, or like that sort of programming, is really helpful. And I think like being knowledgeable about, and kind of basically able to take on some of the new tools that keep being developed. And I'm sure Dr. 𝗪𝗁𝗏 is, or I'm sure everyone's aware, but like there's so much sharing, I guess, in the water technical community. But there's always new like R packages that other people have worked on and are like available to be using. And basically, if you're equipped to take on those new tools, and I think like having proficiency in R and Python is a good example, is really helpful. And ultimately too, it can, for certain complex things, can make you more efficient.
yeah.
Basically, it can mean that you can save time and spend more time thinking about like a deeper thought or like more content to it than necessarily. And then I guess the one other thing too, like for modelers, like I think even if you're not the one collecting the information that you're using, I think it's always wise to have an understanding of where information comes from and be like scrutinize it, sort of like basically be skeptical to a degree and make sure that you're comfortable with the information that you're using. And I think in the growing land of AI, that's sort of ever more like it's always important.
Yeah.
And I feel like it just good to make sure that as a professional you own like the information and the I guess the decisions you make upon it. And so just whether it's field work or remote, like field obtained or remote sensing or reanalysis products or this, that, or the other thing, basically being informed about what it is, what it isn't, where there might be pitfalls, and kind of how you can use it.
Mhm.
But
So we have a few more minutes if there is other questions in the room.
I just have one about your projects or just projects you've worked on. So you were saying that the big one that you spoke about earlier, you started in 2023. Are they usually 1 or 2 years? Or I'm from the agricultural sector, so I'm used to like having to wait for the season to be ripe. So it's at least 3 years to get actual data and stuff. So with your projects, do they usually go longer than that? Or are they usually like 2 years or a year long?
so obviously it takes time to do something of like big substance. I mean, some of the projects that you saw, and so they'll kind of fall into a few different bins. So some are short projects where it's like a relatively brief question, and the information is already available to basically to feed into a model. Other ones, there will be like a long period of like preamble to it. So that the 𝑂𝑣𝑒𝑟 project is a good example there, where I've been involved in that project for 10 years. We did an environmental impact assessment. There's been some other monitoring. Basically, you build a lot of knowledge just through participating in a number of different things. Then the actual modeling portion was 2 months, more like pretty brief. And then the third bin is long-term projects and I'd put, say, the next gen hydrological or the environmental impact assessment one. It's kind of a good example as well as that 𝑠𝑎𝑠_power one, where for an environmental impact assessment in Saskatchewan and Canada, and particularly ones that are going through regulatory review by the Canadian Nuclear Safety Commission, there's sort of prescriptive periods of time that you need for like baseline monitoring, and then there's time to actually do the modeling to do it, and then there's the time for like what you'd call like the residual effect assessment and so on. And so like for those projects is and that one specifically, the environmental assessment has been approved now, but there will still be some hearings for the licensing. And so those ones more kind of in the 3 to 5 year kind of span, but and I've had projects where I worked on for 15 years. But those ones, to be honest, are the ones I like the most, because you over time can have some dominion over like what information gets collected. You can build like a bank of say input data or information, or it means that you can more efficiently do more and more complex things later on. And you kind of get to know the I don't know, the ins and the outs of specific environments.
So Ross, on that, so we've been talking quite a bit about the notion of uncertainty. In modeling prediction, basically you come up with numbers, and of course, decision makers always look for crisp numbers. They don't want you to talk about uncertainty. But of course, we've seen in this class that when we develop hydrologic model, for example, that has been our exercise. There is a lot of uncertainty when you compare your model prediction with observations or errors. And of course, you do Monte Carlo type simulation to come up with a range of uncertainty, and that's generally big. What's your take on this after so many years of working in the industry and with the stakeholders, clients, and how you have handled uncertainty quantification and communication to them?
Yeah, uncertainty is a big part of, and it's always a process to navigate like people communication of uncertainty and walking people through yeah, basically what's the difference between like a forecast this week, a forecast like 2 weeks from now, or a forecast at the end of the century. I mean, we even have some instances for contaminant transport where we've been asked to generate projections 10,000 years from now, which like is a kind of a whole question unto itself, but it's very important to contextualize the uncertainty. I find it very useful to basically just spell out like what is the uncertainty and why. There's usually a reason, like maybe it's like uncertainty in input data that gets propagated through your model. It's uncertainty in, say, climate change projections, like what's your ensemble, what is the range of variability just in the models themselves. Sometimes it can be down to measurement error, even at the source point. Usually, though, there's some way to mitigate the uncertainty or contextualize it at least. So for the environmental assessments is a good example where we usually get like a terms of reference, like from the government or like from the regulatory body that basically says your environmental assessment needs to check these boxes. And there'll be like a number of different like criteria characteristics that basically you kind of read that as like your design criteria sort of thing for how you need to design your model. And you need basically your model design needs to be able to answer those questions. There's also usually what you define as like a base case, like of where you're basically if you're comparing like for a new project, the base case would be if there was no project, what would the environment look like? And then you have like an application case where you kind of stack the project on top of that, compare the difference. And you might also have, I mean, what could be summarized as like a cumulative effects case. So maybe there's some other developments in the region that could happen, maybe not, but you kind of stack that on top. Here we call them reasonably foreseeable developments, but it's basically to provide some context. So like those three scenarios are usually the core, and then usually we run many other sensitivity scenarios to target specific uncertainty. And so usually the progression I take, so I mean, one way of doing it, and I do both, but one way of doing it is to basically consciously say, this is an uncertainty I know. This is like a way that we can kind of assess how sensitive our results are to that uncertainty, and then we can talk about how to mitigate it. So usually when you're structuring those sensitivities scenarios, it'll be like in order to address sensitivity to say variation in climate change projections, or sensitivity to say in water quality modeling for environmental impact assessment, maybe it's sensitivity to uncertainty about the source term for the water quality loading. So what if the water quality is worse than what you anticipate? For water management, like mine water management, sometimes it could take the case of basically what happens if the design flood is the 100-year rainfall event. What happens if a probable maximum precipitation falls? Looking at what that is, and the interpretation of those different cases can vary just in terms of what it actually means. And then, like you say, the other way is to do more like a Monte Carlo or probabilistic approach to understanding uncertainty, and I'd say too, in our like thought progression from the back of the napkin to like a really refined, basically you might start out with something that's fairly uncertain but acceptable for that stage. But then progressively you can typically improve, like decrease uncertainty, I guess increase certainty a little bit, but really just like narrow the bounds by getting more information.
Excellent answer, I would say. You know, but you basically synthesized what I've been teaching in this course and that final statement. You know what? So we looked at uncertainty, how to characterize it, and that sensitivity analysis piece that you said, okay, what controls the uncertainty in that target variable? Let's see if that uncertainty source matters or doesn't. And we've been doing some practice and sensitive analysis as well. And I like the piece of the scenarios. Basically, that way you help your decision maker navigate the decision process by building things on top of things. Rather than hiding uncertainty, sweeping on the carpet. Yeah.
Yeah, and then like from an engineering perspective too, like there's certain uncertainties you never get around, or like but also like it's quite common to design in like factors of safety or redundancy, contingency, for the things like at the end of the line, if you know, or at the end of the line, if you still know that there's uncertainty, you can typically look to design your whatever you're designing to basically weather some, or like accept some of that uncertainty. But I guess that's another approach.
Okay, we are 6 minutes over time now. Please join me in thanking Ross Phillips for coming. Having together.
No, and thank you very much for having me. It's been a delightful conversation, and thanks online too for everybody. Great questions.